Hello everyone. In this video, I would like to talk about linear algebra in Python and show you how to do some simple linear algebra operations. So first, let's start with creating a 2 by 2 matrix. And in order to create a 2 by 2 matrix, we will be using a package. The NumPy package here can be used for this purpose. And we just use the acronym NP here, and we call the array method. So we just need to input the rows of this matrix that we want to create. The first row elements are 1 and 2, and then the second row elements are 3 and 4. And then you can simply verify the matrix we create by printing on the screen. And another example here, just a similar one, but this time we want to create a 3 by 3 matrix. Therefore, we will have 3 rows in this matrix. The elements are given just arbitrary numbers here, 1, 2, and 3, 3, 4, 0, -1, 9, and 10. And similarly, you can just verify the output. So let me run the file, and we can see that the first 2 by 2 matrix is printed, and then we have the 3 by 3 matrix is also printed on the screen. Now let's move on to other examples here. So I will comment the first part here. So let's see. Here we have another example, but this actually gives us an error. As you see, if we don't use the square brackets outside, this will actually give us an error, and you can easily check that. As you see, we get the error message here. So in order to fix this, you need to put the square brackets outside first, and then if you run it again, this time you didn't get any errors. So let's put this aside. Now suppose I want to solve a system of equations, which is a very common problem in linear algebra. And suppose my system is given by these 2 equations here. I have 2 unknowns and 2 equations. So how can we solve this? Using the linear algebra. So in order to solve this, actually you will need to use, again, NumPy package, linear algebra library. We can use this solve function. So only thing I need to do is define my problem in terms of a times x equals to b. So here a is going to be our matrix of coefficients in this system here we are trying to solve. So what's the coefficients? We have the first coefficient equals to 3, and then we have 2, and then we have the coefficient here is 1 and 2. So this is the coefficient matrix, and the matrix of the unknown variables, or the vector actually, is x, which is containing x1 and x2 as the unknown variables here. And the right hand side is what we have here, 5 and 5. So that is our b. So once we define these, input these, then the only thing we need to do is call this function solve and give the matrix of coefficients and also give the vector on the right hand side of the equations. And that's going to give us the result. And if you like, we can again print on the screen and verify. So as you see, the output for x1 is 0 and x2 equals to 2.5. So this is the solution of the 2 by 2 system of equations given. And similarly, you can solve a 3 by 3 system similarly. Just input the matrix of coefficients and input the right hand side of the problem, and then call the solve function. So for example, the next example is showing this. So I have the matrix of coefficients given here, row by row, and then the right hand side of these equations with these numbers, and then I can just get the result in this x. This is one way, of course. The alternative here, as you can see here, our problem is x equals to b. So we can also solve this by x equals to a inverse times b. Okay, this would be a direct calculation by inverting the coefficient matrix A, and this will also give us the result. Both of these methods will give us the same result, but computationally, of course, there are some differences, especially inverting a matrix, especially if it's a large matrix. It's going to be a more time-consuming and expensive operation from the computational point of view. Therefore, it is not preferred to take the inverse of a large coefficient matrix, and you might prefer to use the solve method for computational speed. So if we do both ways, and then we can still compare in this print statement. So here we can compare both results and see if we get the same result from both methods. And as you see, this print statement here shows us x and x2, both of them gave us the same solution. Matrix multiplication, we can use the dot function here. Suppose I have 2 by 2 matrices to multiply A and B. So first we enter the numerical values and create this matrix A, and then we create the matrix B similarly, and we can use MP dot operator here. This is going to do the matrix multiplication as we know in linear algebra. But if we want to do a term by term multiplication, we use this star here. Okay, so that's going to do the multiplication of 1 and 5, 2 and 6, 3 and 7, 4 and 8. So each element in a specific row is multiplied with the corresponding elements in the other matrix. So this is the so-called term by term multiplication. We can quickly verify our result. So as you see, this is the matrix multiplication we get from using the dot function here. And then if we do the term by term multiplication, 1 times 5, 2 times 6, as you see, 5, 12, 21, and 32. So these are this is the second one, is the term by term multiplication result. So they are not the same. Now if we look at another example, which is the inversion of a matrix. If we want to invert a matrix, we use just the I and V function. Basically, this allows you just to invert a function, a matrix, as long as it is not singular. So we just need to be careful. If the determinant of this matrix equals to 0, then it's not going to be invertible. As long as the determinant is not 0, it's going to give us the inverse of the matrix we input. So here our matrix is A, given with these elements, and then we can print and verify what's the inverse for this matrix. And you see the last matrix printed here is the inverse of this matrix A. Another, again, very commonly used operation, let's uncomment this one, that's the determinant. And basically, if we want to calculate the determinant of a matrix, again, we have the function in this linear algebra library. We use the DET and input the matrix that you want to compute the determinant. And as you can see, it's quite straightforward. It's going to give us the determinant of this matrix. It is equal to minus 2, basically, approximately. And you can also calculate this actually analytically easily by cross multiplying and subtracting the appropriate terms. So here's another example for 3 by 3 matrices, and we can, again, this is the matrix multiplication for the 3 by 3 matrices. And you can create various similar examples for the inverse, as you see, the determinant. So these are, again, very similar operations. Just a few additional functions that you can use. If you want to create, let's say, a matrix of zeros with all the elements equal to 0, then you can use mp.zeros. So that will produce us a 2 by 2 matrix of zeros. So you can, again, quickly verify these output, like the last one is the matrix of zeros. Or you can create a 3 by 2 or 2 by 3, it's up to you. Whatever dimension that you want to use, you can just tell the function as an input. The next example here is about the identity matrix. Again, we often need to create an identity matrix, and that is, again, quite straightforward. You use the I method that's going to generate the identity matrix. If you want a 2 by 2, or like, let's put it 4, that's going to give us a 4 by 4 identity matrix, as you see here. The other, as usual, matrix operations, as long as you are working with the matrices with right dimensions, then you can do matrix summation. You can add two matrices A and B, for example. It's going to add the term by term. Or you can consider matrix multiplication or subtraction. These are all commonly used operations that you might need. So we can check. The matrix multiplication of A and B is given here. And if you want to add the two matrices, let's say, so let me save this and run it again. So as you see, the sum of these two matrices is actually given here. That's 6. This is the term by term. 2 plus 6, we have 8. 3 plus 7, we have 10. 4 plus 8, we have 12. And then this one is the regular matrix multiplication of A and B. As we have already mentioned, element-wise multiplication, in that case, you just use the product A times B. That's going to do the term by term multiplication, as you see. 1 times 5 is 5, 2 times 6, 12, and so on. What else? We can also need to transpose a matrix, and for the transpose, you just use this capital T, A dot T. That's going to transpose the matrix A for you. And our matrix A here is transpose. So this is our matrix A. So the first row becomes the first column. The second row, 3 and 4, becomes the second column as a result of the transpose operation. Determinant, we have already did these examples. So basically, these are the operations that you will need to use most of the time.